there is some good news for you. Any guesses?
No midsem.
No, that's for the institute to decide. I cannot decide that at my end. So the good news is bad news for me. Actually, my laptop's battery is dying, so it barely lasts about 45 minutes. And the bad thing is that if I put this on charging, I'm unable to write on the screen. So I'll possibly get a. I noticed this morning while in another class. So I'll possibly get this replaced next Tuesday. So after next Tuesday's class, that is. I don't want laptop. So until next Tuesday, you guys can have shorter classes. That was the good news. So yeah. So let us start where we left off. So in the last class, we defined. Ah, yes. So I'll put this window here. Yes. And in the last class, sample space, events, and event space, right? So let me put this on battery saver automatically. Maybe that will help. Hold on. Battery saver on. Yes, so it's permanently on battery saver. Let's see if this lasts 1 hour. And the event space, right? And had also that probability of singleton events in a event space is continuous sample space, not event space. Is 0. Right? This we had defined in the last class. And as an example, we had considered the case where was the real line, and we had considered event as x is an integer. So now I define another event. You know this set Q? Gandhi, you know the set Q? Shirish?
Rational numbers.
Yes, rational numbers. So by extension, since Shankar, it will be helpful if you can turn off your mic. Thank you. Since not again. Q is basically Q is defined for P over Q with P in agreed?
Okay.
Yeah, so uh, agreed, Shirish, you agree with this?
Yes, sir.
Okay. Saurabh cannot see the screen. Who else cannot see the screen? Raise your hands. Except Saurabh. Okay, Saurabh and one other. So you guys maybe leave the meeting and join again, because if I try to do that, things get messed up. So, and majority can see the screen, so you guys can possibly try once that leave the meeting and join again, and that will help. Yes. So so let's define another event G. X is an irrational. So any guesses on the probability of G?
One.
Yeah. F complement, and since so the probability of we picking an irrational number out of this thing is 1. Fine. So that said, let us move on. And so we had defined the properties of the probability measure last time, right? That is, hold on a second. Let me open that, and I'll, let me open last week's lecture here. So I'll be able to. Oh, so lecture 14. Oh, so okay, so whiteboard lecture 14 SVG hasn't been uploaded properly. Saurabh, you rejoined twice or thrice, but it's not visible, so let me do it for you. So unshare, share again. Saurabh, now is it working? So have we done the properties of the probability measure? Yes, we have. So we have discussed the properties of the probability measure. So now let us define what is known as conditional probability. We define probability of an event E1 conditioned on E2 as E1, it's called given E2 equals probability that both E1 and E2 happen divided by probability that E2 happens. Fine. And let's generalize this. If is non-zero, if E2 is an impossible event. If E2 is an impossible event, then probability of E1 given E2 will be zero because the given event itself is not happening. Now, also, we will not consider the case where, so for the rest of this discussion, we will not consider any zero T events for the simplicity of exposition, but the results can be trivially extended. Fine. So now probability of E2 given E1 can similarly be written as of E1 given, sorry, E1 intersection E2 divided by probability of E1 or probability of E1 given E2, or rather I write it like this, probability of E1 intersection E2 equals probability of E1 given E2 times probability of E2 equals probability of E2 given E1 times probability of E1. If I rearrange these two equalities, what I get is probability of E1 given E2 equals probability of E2 given E1 probability of E1 divided by probability of E2. Fine. Can anyone give me a name for this?
Bayes theorem.
Bayes theorem, yes. So can anyone give me a practical application for this? Actual, sorry?
Earn problems, colored ball from
Navya, practical application. So have you heard of
Detecting a
If we
disease.
received,
yeah, detecting a disease one
if we
and
received communications of
Error
0
correction.
or 1,
communication signal what?
communication of 0 or 1.
Yeah, that's our that's our next course. That's actually our next course. If I teach that.
Error correction, sir.
Again, our next course. How about this guy? How many of you know him? Huh? No one knows this guy. Am I old? Huh? Makes sense. So this, so what he does is he observes the effect. He observes what's on Watson's John's phone, and then uh, list out all the possible causes, choose the most likely cause, and how likely was the cause itself, and use that to choose what was the cause of the effect. Isn't that so? The cause is an event. So why isn't the pen working? So I can say that cause and effect are events.
Yes, sir.
So since cause and effect, so event, cause, or the effect is an observable event. Cause is not. Fine. So now suppose you have an ice cube, or you have an ice sculpture. Can you tell me if I leave it, if I leave that ice sculpture out in the open, how will it look like 5 hours later? Can you tell me? How will the ice sculpture look like 5 hours later if I leave it out in the open? Come on, Navya. Navya? Bala?
Sir,
Yeah. How will it look like? A puddle on floor. Simple. 5 hours, everything will melt off. Isn't it true?
sir.
Yeah, so it'll look like a puddle on the floor. So if I show you an ice sculpture now, you can predict what it looks like 5 hours from now. But if I show you a puddle on the floor, can you tell me what did the ice sculpture look like?
A shape we can't predict.
Yes, you cannot tell me the shape. So that's why this cause is not observable. The cause of that puddle won't be observable. So we are likely to, uh, or this is how deduction works, that you have a cause, you have an effect, and you choose the most likely cause. Choose the cause that is the most probable cause that effect. Fine. So I'll give you another example. I thought of this as an exam problem, but let's not take this as an exam problem. Some Bala, you said detecting diseases, right? Or someone else said detecting diseases. Who said detecting diseases?
Sir, I see.
Okay, I it didn't show up on my screen. You can
Sai
possibly
Raj.
Sai. Okay, great. Sai Raj. Okay, Sai. So I hope your friends call you Sai, because Sai Raj is 2 syllables, or they call you Raj.
First one.
Okay, your friends call you Sai. Excellent. So Sai, uh, there was a proposal some 3 years ago. Some nice people at GNRC. You know GNRC?
No, sir.
Okay. Okay, GNRC is a Guwahati Neurological Research Center, and it's called Guwahati Neurological Research Center, and it's just behind the IIT campus. So maybe when you guys are back, you can go visit there. So some nice people at GNRC, since it's a neurological research center, what they contacted our department for was that they want to develop uh, an implant that would so some epileptic seizures or some brain functionality would be so ev- everything in the brain works via electrical impulses. Agreed? So they wanted, so when the impulses are improper, you or there are not sufficient impulses or there is some electrical disturbance, you can have epileptic seizures and such episodes. So what those guys wanted was that let's have a system where you can, if since electrical impulses can be controlled all the time, that's what electrical people do. So let's implant a device in your head that will detect when these electrical impulses are getting problematic and counter these via generating cancelling electrical pulses. Fine? Sounds good on paper? Now this approach, yeah. Anyone said anything? Okay, cool. So this sounds good on paper, but this thing had two parts. One, detect when there was a problem. So sample the space every second, possibly, and find if there a problem. If there is a problem, take corrective action. So this kind of problem occurs once in months. So once in months means that so a month has 30 days. How much is this in seconds? So I'll do that quickly using a calculator. So about 259200 or so the approximately I'll write it 2.5. The probability of this event an electrical imbalance event is approximately 1 by 2.5 into 10 to the power 6 approximately 10 to the power -7. Fine. And now if we have a device that is 99% accurate, then 99% of the time it will properly detect this issue and send correcting impulses. Fine. So I can save 99% of the people. And is there a problem with this? Or can anyone identify the problem with this 99% accuracy?
What if it takes a correct signal as wrong signal?
Precisely. Precisely. That is the problem. So this is 99% accurate means one % of the time it will generate an electrical response when there is problem. That will fry your brains. That will literally fry your brains. Now let us calculate the probabilities. So let E be the event that there is a problem. F be the event problem is detected. 99% accurate means P, we know that PRE equals what? We know that 4 into 10 to the power -7. Also, accuracy means probability of E complement, sorry, probability of E given F equals 0.99. Probability of E complement given F complement equals 0.99. Probability of E given F complement, sorry, F given, sorry, my bad. E given F, not F given E. F given E and F complement given E complement. Probability of F complement given E, that is you do not detect anything when there is a problem, is 0.01. Probability of F given E complement is 0.01. So we have to say we are interested in the probability the device frying your brains, which is probability that E complement given F, right? Nothing happened and you took an action, which equals probability of E complement and F divided by probability of F. Fine. Equals. Now E complement and F. F equals 1 minus 4 into 10 to power minus 7 times sorry. Probability of E complement. So this is the numerator equals probability of E complement given F. Sorry, F given E complement times probability of E complement equals 0.01 times 1 minus 10 to power 1 minus 4 into 10 to power minus 7 equals approximately 0.01, right? Approximately this will be 0.01 and probability of F equals probability of F given E plus times probability of E plus probability of F given E complement times probability of right. This equals 0.99 into 4 into 10 to the power minus 7 plus 0.01 into 1 minus 4 into 10 to the power minus 7. So this means that you can again see that this is again close to 0.01. Therefore, probability of E complement given F, that is the device takes action when there is nothing wrong, or yes, the probability that an action was taken when nothing was wrong is 0.01 divided by 0.01, quite scarily close to 1. In other words, it'll fry your brains with 1% probability every second. So with a mean lifetime of 100 seconds, everyone using that device is dead. Whereas they have a fair chance of surviving across multiple months in the event of no such in the absence of that device. And when I tell you that the device is 99% accurate or 99.9% accurate, you are or when a salesman tells you that this device is 99.9% accurate, you are more or less happy to have it for you, right? So anything, uh, any insight that we gained out of this? The first one is that always look at the mathematics and don't only go for the sales pitch. So now the next thing is independence. Two events I'll call them E and F now, are said to be statistically independent if occurrence of A does not affect the E, talking about E and F, that is probability of E given F equals probability of probability of F given E equals probability of F, and by extension probability of E intersection F equals probability of E times probability of F. Fine. And events are called mutually exclusive if E intersection F leads to the null set. Fine. Any questions with this? Great. So with these definitions, with these definitions of conditional probability out of the way, we are now in a good position to define the next major topic that we will discuss. Random variables. So I'll write this down for you. Variable is mapping from the sample space to the and denoted using uppercase letters from the Roman that is X, a random variable now. First thing, notice is, hold on. Yeah, is like this. Oops. Sorry. Random variable is like this. What is it? Random variable is like, hey, what happened? Hold on. Copy image. So yeah. So a random variable is like this desert. So the desert is coming. Hold on. It's yeah. So what is this desert called? Gandhi, what is this desert called?
Gulab jamun.
Gulab jamun. So why is a random variable like a gulab jamun? Is it gulab? Gulab means rose in Hindi. Is it gulab? Is it jamun? Everyone knows. Jamun. Is this gulab or is this jamun? Shirish?
No, sir.
Yeah. So similarly, a random variable is a mapping from the sample space to the real line. So a random variable is a mapping. Mapping means it is a function. Mapping is this is how we denote functions. Random variable mapping. That is, it is function, and function is clearly not a a function is not a variable, right? So a random variable is not a variable. Also, if say I toss a coin with the sample space, then if I allocate the random variable x of h equals 1, x of t equals 0, then every time I get head, I write a 1. Every time I get a tail, I write a 0. So this then is a deterministic mapping from. Had it been that if I get a head, I allocate a 0, and I at sometimes I represent it with a 1, at sometimes I represent it with a 0, then it would have been random. Isn't it so? That is what is random. This is a deterministic mapping from the sample space to the real line. So we can conclude, therefore, that a random variable is neither random nor a variable. Any problems with this statement? That a random variable is neither random nor a variable. So with this information with us, we define the following terms. A random variable is called discrete if its range can be mapped onto a subset of Z. Random variable is called continuous if its range is an uncountable set, sorry, subset fine. With this information or with this set of tools, we are now ready to define the next beast that we call as the cumulative distribution function. So whenever I write random variable, I'll write a random variable. Whenever it is, I shorten the random variable to RV since R starts with R. So I'll write an RV. So it's the way you read it, or it's all in the way you read it. Fine. So the CDF or the cumulative distribution function of a random variable is defined as fx of small x equals probability that such that x of omega less than or equal to small x. So this capital X, I'll just deconstruct this notation here because this gives us a lot of trouble all the time. So let's deconstruct this notation. Variable that talking about a dummy variable whose value is greater than the random variable that are greater than or equal to. Fine. So, and for simplicity, for the rest of this course, we'll simply write I hope you are comfortable with this notation due to your probability course, and I'll relist the properties of the CDF. Properties of the CDF. One, fx of x is a non-decreasing function. Small x. So you know the difference between increasing and non-decreasing, right? I take that as a yes. So wherever there's a problem and you are not sure about something, please say it out aloud. Otherwise, I assume that you know it and I proceed. Limit x tends to infinity, fx of x equals 1. Property 4, limit x tends to infinity, sorry, x tends to minus infinity, not infinity. Minus infinity, fx of x equals 0. The CDF is right continuous. That is limit epsilon tending 0 plus f of x, x plus epsilon equals not epsilon tending 0 minus probability a less than equal, sorry, less than x equals x of a 5, 6. This should be 6, not 4. 6 and 7. Probability that x equals a equals fx of a minus, or fx of a plus minus fx of a, and use the CDF to define the probability density function of a random variable as fx of x equals d by dx. So this is d by dx of small x, that dummy variable, with the following properties. So I'll list these properties and stop. It's non-negative. So if you want this to be a lose inequality at both ends. Obviously, if I remove this, change this b plus to b, it will be this. So a to b this, then a plus and b plus you can probability that x variable is contained within some set A equals probability or equals the integral small x in A fx x dx. CDF equals x. Fine. So I'll just number these properties 1, 2, 3, 4, 5, and yeah. So these 5 are the properties of the PDF probability density function, and we have listed the properties of the CDF. Now, next time, we'll talk about functions of random variables. So, any doubts, problems, etc.? If none, then we can possibly stop and continue tomorrow. Great. So, and the good thing is that with battery saver on, my laptop lasts 1 hour. So we'll stop here. Thank you. Bye. Have a nice day.
Thank you, sir.
Have a nice day, sir.
Thank you, sir.